Hi everybody, this is day 3, sets, Venn diagrams, and the addition rule. Sets are going to be the first part of the lesson, very simple, so I'll kind of breeze through that. Venn diagrams are mixed throughout, and the addition rule is what I'll spend more of my time on. A set is a collection of things, numbers, objects, etc. What's contained in the set are elements. So for example, in example 1, the set A is defined as a collection of all integers that are greater than 0 and less than 10. Integers are whole numbers. So greater than 0 and less than 10, I would say the set A, we're calling it, A is the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. They're greater than 0 and less than 10. So that's a set of numbers. If I write it as a Venn diagram, this might look like a strange Venn diagram. This is set A. All of the numbers would be in the bubble here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's no numbers that are not in the set A. A subset is any set whose elements are contained within another set. So, for example, set B. Let's say we've got odd numbers. That's what we'll do. That is a set, or a subset, excuse me, because it's a set of numbers within a given set. So odd numbers would be a subset, a smaller set from this big set. So I would say that the odd numbers are 1, 3, 5, 7, 9. Another subset example could be, for example, multiples of 3. So if I look at the full set A, the subset, the smaller set, multiples of 3, would include the numbers 3, 6, and 9. So there's 3 sets, or 3 elements in this subset. Each piece in a set or a subset is called an element. So 1 is an element of the subset, 7 is an element of this set A, for example. So those are basics. If there's nothing in common for a set, you would use the empty set. So let's say if I said, instead of odd numbers or multiple of 3, I would say numbers greater than 9. Well, there are no numbers greater than 9. So if there's nothing in common, you would use the empty set symbol, which would be empty braces, or that O with a slash through it. So we're gonna move on to another example of sets, because that's pretty simple. If you go to the next page, consider rolling a single-sided die and recording results. Let set A be the event of rolling a number greater than 4, and B is the complement of the set. Remember from day 1, the complement is what's not in this set. So basically, what's not greater than 4. So we're gonna embed some Venn diagrams and some elements from previous lessons. So we've got set A and set B. I'll mark them. Set A, they said, was numbers greater than 4. Well, if we're rolling a die, the only numbers greater than 4 are 5 and 6. And those are just in set A. It's not in set A and B, so I wouldn't put it in there. Set B is the complement of set A. So remember, the complement of set A is, again, what's not in set A. So on a 6-sided die, what's not 5 and 6? The numbers 1, 2, 3, and 4. So we have set A, set B, they have nothing in common. So if I want to find the probability of choosing an element from A, set A that is, there's 2 numbers out of 6. And we can also say 1/3. Oftentimes in probability, you'll notice that numbers and fractions are not reduced. And the reason why is because 2/6 is more descriptive of what's going on than 1/3. 2/6 tells me exactly 2 out of 6 numbers fall into set A. 1/3, again, is equivalent to 2/6, but it's just not as descriptive. What's in set B? There are 4 elements out of 6 in set B. Remember, this symbol here means intersection. So intersection means this little crevice in here. There's nothing in the intersection, okay? So there are no numbers. The probability of this happening would be 0 because there's no way to choose something in the intersection because there is nothing in this intersection. So the probability something can't happen is 0. What is the sum of the probability of A and B? Probability of A, we said, was 2/6. Probability of B is 4/6. You could use the reduced fractions as well. Oh, and I didn't reduce it here. It would be 2/3. I would get 6 out of 6, which is 1. And that makes sense because it's both things added together. Part D says, prove that the sum of the probability of an event with the probability of its complement will always be 1. I'm going to use a different example than what I'm using here. So this is just saying, let's say the probability that it's going to rain is 0.7 or 70%. Okay? The complement, I'll say rain, that little C up there, remember that means complement? That means everything that's not in this set. So if 0.7 is the chance of rain, then 0.3 is the chance that it will not rain. I always just stick the word not in front. The probability is rain, then the complement would be not rain. Together that is 1. Okay? So if I did rolling a fair die, let's say rolling an even number is 3 out of 6. If I want to find the complement, I could say like, E with that little C up there as a complement. But that just means in our terms, not even. Again, I just stick the word not in there. So rain, complements not rain. Rolling an even, complements not even. And that will give me 3 out of 6. And together that makes 1 or 6/6. So next up, we're going to get to adding probabilities. So I go to the next page here. So I'll start in with this example at the top. Example 1. We've got a spinner that's divided into 8 equal sized sections of a circle. We're going to spin the spinner once. A is the probability we'll land on even. B is a prime number. Remember, a prime number is divisible by 1 in itself only. And so I'm going to start filling this in. I'm going to go one number at a time. The number 1 is not even, but it's not prime. The number 1 is not prime, nor is it composite, so that's going to go in this outside area. The number 2 is even, and it's prime. It's only divisible by 1 in itself. So it goes in the intersection. The number 3 is not even, but it is prime. The number 4 is even, but not prime. 5 is just prime. 6 is even, not prime. 7 is just prime. 8 is even, but not prime. So I've got 3 elements that are just even, 1 in the intersection, 3 elements that are just prime, and 1 that is neither of the cases. So we'll use these numbers below now. In here, this is just, again, a reminder, a refresher of what union and intersection is. The union is when you combine things. Think of a marriage when you guys, if you guys get married, if your parents are married, the union means that both sides are brought together, both families brought together, etc. The intersection is just what's in common, and those are the symbols, again, respectively, for each. So in example 2, we're going to use the example above to write out the following 2 sets. A or B. Again, that's the union, A or B. So A or B, the set of numbers that are in either A or B would be 2, 3, 4, 5, 6, 7, 8, all those numbers in the bubbles, okay? Because it can be in this one or in this one, doesn't matter. Remember, A is even or B is prime. So if I said I want all the numbers that are either even or prime, I can choose 2, 3, 4, 5, 6, 7, 8. Intersection is just what they have in common. So that's up. Oops, I wrote the wrong symbol in there. It's that upside down U. So intersection is just 2. That's all they have in common. Okay. So now let's look at this equation here. The probability of A or B equal to probability of A plus probability of B. It seems like it would work there, but let's look at this, guys. The probability of A or B, how many elements are there? 1, 2, 3, 4, 5, 6, 7. So there are 7 out of 8 numbers in the union of P and B. The probability of A, the probability of finding just an even number would be 2, 4, 6, 8, because those are all even numbers. So that's 4 out of 8. And probability of B, prime numbers would be 2, 3, 5, 7, so that would be 4 out of 8. So you can see these don't equal each other here. Sorry if I was off the page for a second. 7/8 does not equal 8/8. And the reason why, you may have spotted it already, is because we counted the number 2 twice. We counted the number 2 as an even number, which it is, and we counted it as a prime number, which it is. So when this scenario happens, when there's a piece of information or pieces of information that overlap, we have a formula to help us figure out their probabilities. It's called the addition rule. So the addition rule is used when there are common elements. Like the number 2 was an intersection. It was like a common element to both set A and B. So we're going to use this when elements are in common. So let's take a look at example 4. We've got a 6-sided die rolled once. Find the probability that a number rolled was either an even or a multiple of 3. Well, let's take a minute here to think about what are our even numbers. And we could represent this as a set here. We could use a Venn diagram. But even numbers on a 6-sided die would be the numbers 2, 4, and 6. The next one was a multiple of 3. So multiple of 3. The numbers that are multiples of 3 are 3 and 6. So if I wanted to find the probability of getting an even, or I'm going to use M for multiple of 3, I'd have to use this formula because there's an element in common. If there's one element, 2 elements, anything that's in common between 2 sets that you're looking at, you need to subtract out what's in common. So to find the probability of one or the other, I'd find the probability of getting an even. So probability of getting an even number is 3 out of 6. There's 3 elements out of 6. Plus the probability of getting a multiple of 3. There are 2 out of 6. But I've got to subtract out what's in common, which is 1 element in common. So the probability of getting an even and a multiple of 3 would be 1 out of 6. Now, in this instance here, some of you may be able to do this without the formula. This is just getting you to recognize that there's something in common here. So if I just said what's an even or a multiple of 3, some of you may have looked at the numbers 1 through 6 and said, okay, what's even or a multiple of 3? The number 2, 4, 2, 3, 4, and 6. So you might just say, well, there's 4 numbers out of 6, and just count it up that way. This is doing the same thing. 3 plus 2 minus 1 is 5. So let's take a look at another example now. Example 5. Insurance companies typically try to sell many different policies to the same customers. At one such company, 56% of all customers have car insurance, 48% have home insurance policies, and 18% have both. A customer is picked at random. So we want to find the probability that she or he has at least one of the policies. So we're going to find the probability that they're going to have a car insurance policy or a homeowner's insurance policy. So we want to find the probability they have car insurance. plus the probability that they have a homeowner's insurance. And since there's an area that's in common, we want to subtract that out. So probability of C and H, car insurance and homeowner's insurance. So probability they have car insurance is 0.56. Probability they have homeowner's insurance is 0.48. We subtract out what they have in common, 0.18, and the probability is 0.86, or an 86% chance that would happen. Part B, find the probability that she or he has neither of the policies. So the probability they have a policy, probability that they definitely have a policy is 1. Subtract out the fact that they have neither of the policies, so probability of C or H. 1 minus 0.86, we just found that, is 0.14. So that's probability they have neither. If that's a probability of C or H, and we want neither C or H, it's 1 minus this number. So 0.14 is your answer there. Okay. You might be thinking also of Venn diagrams. This could also be represented as a Venn diagram where we have to create our bubbles here, car insurance, homeowner's insurance. We label what they have in common first in the middle, 0.18. That's 0.18 in there. It's sort of small from your point of view. We would say then 56% of the customers have car insurance policies, but remember 56% or 0.56 includes this number here, so we'd have to subtract that out. So 0.56 minus 0.18, and we would have 0.38. Those are the number of people that just have car insurance. Homeowners insurance, we would say there's 48% of the customers that have homeowners insurance, but we need to subtract out the 0.18, which is just 0.3. And then if you want to find out the neither, again, you could add up these numbers, subtract it from 1, and you would get 0.14, which is neither. Again, all of these probabilities in a Venn diagram should sum to 1. That's it for day 3, and Mr. Kenzie will have the homework answers up next.